All right, let's talk about the computers you don't see. We're going to pull back the curtain on the millions of tiny, invisible computers that are quite literally running our world.
I mean, have you ever stopped to think about it? How does your smartwatch actually know how many steps you've taken? Or how does a car's engine adjust its fuel intake in a fraction of a second? It feels like magic, but it's not.
The answer to all of this is something called an embedded system. It's basically a dedicated, specialized computer that's designed to do one specific job and do it perfectly thousands of times over.
So, what's the secret sauce here? How do they all work? Well, it turns out pretty much every single embedded system out there operates on a really simple but incredibly powerful three-step cycle.
And this is it. First, the system uses a sensor to sense something about the physical world, maybe a temperature, a button press, you name it. Second, it processes that information using its software to make a decision. And third, it acts on that decision. Maybe it turns on a motor or flips a switch. Sense, process, act. That's it. This is the fundamental heartbeat of the entire embedded world.
Okay, so at the very center of this cycle, you've got the hardware, right? The actual physical brain doing the work. And that brings us to the microcontroller.
A microcontroller, or MCU for short, is pretty much what it sounds like. It's an entire, self-contained computer that's been shrunk down onto a single tiny chip. But it's not made for browsing the web or playing games. It is highly optimized for one thing: control.
Now, you've probably heard of a microprocessor. That's the big CPU at the heart of your computer or your phone. The key difference here is that a microprocessor is just the brain. It needs a whole bunch of other separate chips for memory, for input-output, for everything else. A microcontroller, on the other hand, is the whole package. The brain, the memory, all the peripherals, it's all integrated right onto that one chip.
And this is what's inside that all-in-one package. You've got the CPU, which does the actual thinking. You've got memory to store the instructions and data. And then you have these things called peripherals. You can think of peripherals as the chip's built-in senses and limbs. They're the tools that let it talk to the outside world, to read a sensor, control an LED, or send data over a wire.
So we've got the brain, the hardware. But a brain isn't much use without any thoughts, right? It needs instructions. And that brings us to the soul of the machine, the firmware.
And this is maybe the most important thing to understand about writing that software. It is a game of extreme constraints. Your PC has gigabytes of RAM. An MCU might have just a few kilobytes. That's not a typo. Every single byte of memory, every single processor cycle counts. Efficiency isn't just a nice-to-have, it's everything.
And that desperate need for efficiency is exactly why you see these specific languages used over and over again. C is the absolute king of the hill because it gives developers that direct, low-level control over the hardware. C++ often gets used when you need to build more complex software architectures. And a really interesting newcomer is Rust, which is gaining a lot of traction because it's designed from the ground up to prevent a whole class of nasty memory-related bugs.
Okay, so you've picked your language. Now what? How do you actually structure the software? Well, you have a pretty fundamental choice to make. Are you going to run your code directly on the hardware, what we call bare metal, or are you going to use some kind of operating system?
This table lays out the options really well. On one end of the spectrum, you have bare metal. Your code is the only thing running on the chip. It's super fast, super lean, but it can get really tricky to manage if your device has to do a lot of things at once. That's where a real-time operating system, or RTOS, comes in. Think about a drone. It has to fly, navigate, and communicate all at the same time. And RTOS acts like a super strict traffic cop, making sure the most critical tasks, like, don't fall out of the sky, always run exactly on time. And then for really complex devices, like the infotainment system in your car, you might even use a full embedded OS, like Linux.
Of course, making all this stuff work isn't always easy. This constant dance between the physical hardware and the software running on it creates some really fascinating challenges for the people who build these systems.
Yeah, let's talk about debugging. Imagine you write a simple piece of code to blink a light. You program it onto the chip, you power it on, and nothing. The light just stays off. So what's wrong? Is there a bug in your logic? Did you configure the hardware pin incorrectly? Did you maybe forget to turn on the right clock source for that part of the chip? See, in the embedded world, a software bug often looks exactly like a hardware failure.
To solve these mysteries, developers have a special toolkit.
They can get the chip to send out simple text messages over a wire, kind of like print statements. But the real heavy hitter is a hardware debugger, using an interface like JTAG or SWD. This is like a secret backdoor into the chip. It allows a developer to literally pause the processor at any point in the code and peer inside to see the exact state of everything. It's an absolute game changer.
And as more and more of these devices get connected to the internet, another massive challenge rears its head: security. Because every single connected device, from a smart plug in your wall to the electronics in your car, is now a potential doorway for an attacker.
And that's why security can't be an afterthought. It has to be designed in from the very beginning. This means things like Secure Boot, which is a process that makes sure the device is only running authentic, trusted code. And remember those powerful debug ports we just talked about? It is absolutely critical to lock those down before a product ships, or else you're just handing attackers the keys to the kingdom. So there you have it. We've gone from that simple sense, process, act loop all the way to the complex dance of microcontrollers, firmware, real-time operating systems, and security. These little hidden computers truly are the unsung heroes of our modern technological world.
So here's a thought to leave you with. The next time you use any kind of smart device, whether it's your microwave or your car, just take a second. See if you can picture that tiny computer on a chip, buried deep inside, just running its loop over and over, sensing, processing, and acting to make it all work.